Yes.
Do you have any idea as to why it smells this crappy inside here?
Yeah, they're painting. I walked in here and I said like the same thing. I was like, plug your nose. If you have scented candles, teleport them to your hands and please light them. But yeah, no, I'm also unhappy with that. All right, so we covered parallel lines, a little bit of line segments, and now we move on today to geometry with shapes that are more than 3 sides. Parallelograms, polygons. I guess polygons would probably be 4-sided polygons would be the best description for that. So, when we talk about a polygon, first close the door. Maybe we'll leave it open just a little bit so we can hear. So when we talk about a polygon, there are, we define them as something that sits on a full plane. Polygons do not exist across curving around a plane. So, for our reference today, my plane will be our 2-dimensional whiteboard. So, example of a 3-sided polygon that you have seen. Basic triangle. Polygons with more sides can be drawn I'll try this one more time. Hopefully the pen will not die. Polygons with more than 4 sides, or three or more sides, can look like this. Six-sided polygon, as an example. 4-sided polygon. So there's a couple rules when we say something is a polygon, and they are as follows. So when we talk about a polygon, we define it with some points to start. A polygon has to have direct line segments connecting each point. It can't do this. Not a polygon, okay? Not a straight line segment connecting 2 points. So, our second one is that a polygon cannot have like what you think of as like overlapping sides. This is not a polygon. And then my other pen dies on me. Is the red is good, people? In the back, red good too? Okay. I think I'm gonna switch to red. So, polygon can't have overlapping sides. And then when we talk about a point on a polygon, there is one requirement. So, out of chairs. Sorry. I need that recording now. Completely out of spot. I have 1 chair, not 2 though. Here, I can go grab 1. Chairs. Yeah, just you're gonna I'll go grab it as well. I can grab a pen. Unfortunately, we can't move the iPad. That's the only sad part. Okay. Okay, past the interruption, really quick, back to polygons. So, in this example, we can say A, B, C, D is polygon. That's fine. A, B, C, E, D, A, or sorry, A, B, C, D, A, B, C, E, D is polygon. We can't say that A, B, C, D, E, C, D, A, B is not as a polygon. On top of using a couple points twice, a side has to have exactly 2 edges and no more. So, then there is one other requirement for a polygon. So this is not a polygon as well. Our last one is, let's do that. So, in this one I could say that A, B, D, E is a polygon. I cannot say that A, B, C, D, E is a polygon because a point has to define 2 unique lines. So this BD is a line, BCCD is the same line segment, so it has to be collinear. Consecutive sides need to be non-collinear. Not that they have to be collinear. Okay? So, not a polygon. Alright, so really quick for naming schemes of polygons. The best way to name a polygon is to pick a bunch of points. Why? So, for naming a polygon, the best way to name a polygon is to pick one side. Does not matter which point you start. Go in either clockwise or counterclockwise order till you get back around to the start. So, I'll start from A and say this is polygon A, B, C, Q, R, Y, X, I, W, J, and V. Or A, B, J, W, I, X, Y, R, Q, C, D, A. So, any of those are fine. You can, again, start from any point, go around either direction. Avoid naming points twice, like I did on that last one. So, with that, you can name pretty much anything irregularly shaped. So, one thing to know about an assumption that we make in geometry is that polygons are convex. So convex, convex polygons, they have interior angles less than 180 degrees.
What?
Okay. All right. Okay. So, convex. Convex. So, convex basically just says interior angles are less than 180 degrees. Okay? So, as an example, I drew a very irregular looking hexagon. But if we pick any singular interior side, they're all less than 180 degrees. They aren't straight lines. An example of one that is not convex would look like this. Where this goes all the way around. For geometry, we're going to assume that when I say like create a polygon, it should be non-convex. So it should look like this. Or sorry, they should be convex. They should look like this. They will not be non-convex polygons. So, I'm going to redraw this for one day. So the next thing we can talk about too is the diagonals. So diagonals, we can go from like any point to any other point. Diagonal. Here's some diagonals. If my hexagon was a little bit better. For a pentagon, you get that familiar. Oops. For a pentagon, you get a star. If I could draw a good pentagon. So you could do pentagon, hexagon. So we talk about diagonals. They basically connect any vertex to any non-consecutive vertex. So anyone that goes basically that isn't already a line that's on the outside of the polygon would be a diagonal. Would you guys like the definition for that? Segment two non this could also be non-adjacent if you want to think about that. Non-consecutive, non-adjacent points of You good on that? Okay. So instead of just calling everything arbitrarily polygons, there's probably some of the things that you've already seen named before. I'm just going to cover them all. So when we say a polygon has four sides, we say it's a quadrilateral. Quadrilateral, four sides. Our next one is a parallelogram. So a quadrilateral is just, it has four sides. A parallelogram says that it has two sets of parallel lines. So if we said this line segment was AB, this line segment was CD, AB would be parallel to CD, and then CA would parallel to BD. Okay? So really quick. Just to make that clear. A, B, C, AD is parallel to CB. AB parallel to CB. Okay, so it's basically a special type of quadrilateral. A rectangle. Really testing my drawing skills today. A rectangle is, again, type of quadrilateral. We say a rectangle is a rectangle because it has interior angles of 90 degrees. So you could say that a rectangle is a quadrilateral, a rectangle is a parallelogram. It's just a special type. You can't say the reverse, by the way. Not all quadrilaterals are rectangles. Example right there. But every rectangle is a quadrilateral. Okay? So, our next one is a rhombus, which I will now butcher. Okay. Oh, I'm not sure. Try this one more time. Looks very close to my parallelogram. So, the way we define a rhombus, oops. We define a rhombus as a parallelogram with at least two consecutive sides being congruent. So, all right. So the easiest way to imagine a rhombus, we haven't covered it, it's a square slightly skewed. Okay? Imagine pushing the top line over. So our next one is a kite. I will. So, a kite basically can look like two scalene triangles, if you were to draw a line between them. So it has two sets of congruent sides, and it'll look like that. Are we good on the convex and diagonal? I'm going to erase them for the... Okay, our next couple are the easier ones you've probably already seen. Square. Square is a parallelogram that is technically both a rectangle and a rhombus at the same time. Okay? So the official definition for a square is a rectangle and rhombus combination. The easiest way to combine those definitions is they have four consecutive congruent sides that all have 90-degree angles. Okay? So, so really quick, I'll write this one because it's a little bit different. Both a rectangle. Okay, this next one, trapezoid. So, our trapezoid, we have two sets of parallel lines. And we call them the base, but the other lines a little bit different. So, trapezoid. So then we have one special type of trapezoid. Do you guys remember isosceles triangle? You should shake your head yes, even if you don't remember. There we go. You're making me feel better now. Okay. An isosceles trapezoid is a trapezoid where it basically has, it's a little bit skewed version. It has non-parallel legs, so it's a little bit different. ISOS. I'm gonna butcher this one. I'm gonna butcher this one so much. Close. Okay. Just to make this a little bit clear, I'm gonna use these are considered the legs. This is the base. Sorry, I'll label it. And then legs. So when we talk about this, we say these are the lower base angles, and these are the upper base angles. So these are congruent. Or sorry, I'm crazy. Those are not congruent at all. These are congruent in our isosceles trapezoid. Is there any question on any of these shapes and how we define them? Yes.
What's the definition for a kite?
A kite? A kite, basically, you can think about it as there's two sets of congruent sides, and then it'll generally look like if you had a triangle mirrored across its center line. So this will always be a perfect straight line. Oops. If I could draw well, this would always be a perfect straight line, and you could mirror it across the side. Okay, really quick, quad, yes.
What's the difference between a trapezoid and an isosceles trapezoid?
Generally not a lot. It's very rare to find trapezoids that aren't isosceles, because it's hard to get parallel lines without congruent segments. You can do right trapezoid. That's a good example. But generally, you're getting losing my mind here. Generally, generally when you draw them normally, if you guys ever use those wood blocks when you were a kid that have the red trapezoids, they'll look like isosceles trapezoids. But yeah, there's right trapezoids as well. Here's what a right trapezoid will look like, just for the record. Just has two right angles. Okay. So, are we good on this? Because I'm going to erase it. Okay. So, okay, really quick, we're going to do one practice problem. Call these H-O R and M. Okay, so we're going to do a couple of these. First of all, what shape does this look like?
Parallelogram.
Perfect. So, if I said this is a parallelogram, are all four sides congruent?
Not necessarily.
Not necessarily. Okay. Are the diagonals exactly perpendicular? Not necessarily. So I'm going to adjust it real quick. I'm going to try and do this a little bit better. One more time. Okay, it's closer. Okay, I'm gonna say this is a rhombus now because you probably couldn't tell if I drew it. So this. Do the diagonals bisect each other? Yeah, I wish I'd drawn it better. I'll make this a little better. Give it one more try. One more try. Cool. Okay. Rhombus. Attempt 3. So do the diagonals bisect the angles? Yes. Yes. I like it. Do the diagonals bisect the angles? Do the diagonals bisect each other's line segments to exactly half? Yes. They do, yes. They do? Yeah. So, with our rhombus, really quick, are all four sides congruent? They are in a rhombus for this one. Then, are the diagonals exactly perpendicular? I'm slightly off in my drawing, but they are, I promise. Then, the diagonals bisect the angles? Yes, they do, because our sides are all the same length. Then, do the diagonals bisect each other? They do. And finally, are the diagonals congruent? Not necessarily. Maybe. Okay. We are going to pull up more fun questions. I'm guessing these are not very fun to watch me fail at drawing. So, okay. So, I'm going to give you a little bit of a way to calculate something. So, here's my rectangle. I'll call it A, B, C, D. Here's my rectangle. Well, how do you calculate the area of the rectangle? Base height, perfect. B, H. Okay. I'll try this. This will be a parallelogram, I promise. E, F, G, H. Okay, how do you calculate the area of a parallelogram?
The base has altitude.
Base times altitude. Yes. Do you guys know why this works? I'm going to take that as blank stares as no. Okay. I'm going to do it down here. But to prove to you that this is not just some crazy thing that I will yell at you. So, let's say this is the base times height. We'll give it some numbers to Show that we're not crazy. So, really quick, let's give this a value of 10, let's give this a value of 5, and say, bam, the area is 10 times 5 or 50. Okay? So, on this parallelogram, I'm gonna tell you that this is 10 and this height is 5. So, the way this works is, I'm gonna draw it down over here one more time. And be even worse than before. Man, I should have taken art classes. Okay. So, first one, yes, right? I'm gonna say that I told you this distance right here was 10, yes? And I told you that this height was 5. So, what I'm gonna do is I'm gonna take this part right here. We're gonna use scissors. I'm gonna snip it. I'm going to put it right here. So, it's now going to look like this. Remember, oops, write that there. Remember, I told you this height was 5. This is a nice straight line segment. I told you this length was 10. Did I change the length by moving this over here? On the bottom? No. Did I change the height at all by adding something up or above? No. So that's how calculating the area of a parallelogram is technically base times, yeah, we'll use altitude, so we'll use BA, which could also be Berkeley Academy. Okay, area. Mark there. So, that's how calculating the area of a parallelogram is pretty much exactly the same way to calculate for the area of a rectangle. It works the same way. I wish I had paper. I would say that we could go grab scissors and cut these up, but that is okay. So, we are going to do one more problem before moving on. So we're going to prove that the diagonals of a rectangle are congruent. Okay, so proving that the diagonals of a rectangle are congruent. I'll let everyone think on it for a moment. Just wait. if anyone else is melting like me. Okay, are we ready? Do you have an idea what we want to do? Thought about it? Another minute? Think about it a little bit more. Proving that these diagonals are congruent. I promise this is not a square, by the way. It's a rectangle. Thirty seconds. All right. Ready to go? Proving the diagonals of a rectangle are congruent. Anyone, step one.
You can make two triangles ABD and ABC. So you should yes, AB.
Okay. You said ABD? Is that right? Okay. Okay.
And they share AB and use a structure property. ABC is AB.
I'm just gonna. Okay.
And then
I like it.
angle DAB and ABC are equal because it's a rectangle. It's a rectangle and they're all sides are all angles are 90 degrees.
Okay. I'm gonna get them all in one shot, actually. CA is equal 90 degrees. I'm just gonna give it all in one line. I'll call this property of rectangle. Okay.
And DA and CB have to be congruent because rectangles they have two sets of parallel lines.
You're saying DA and CB? Okay, I like it. I'm gonna move on this side really quick, people.
And because SAS you can say triangles DAB and ABC are congruent.
Perfect. Okay.
And if you use CBCTC to
I like it. Then we can say AC is congruent to DB. CPCTC. You get that? Makes sense? I will run through it in one shot. So, just to be real clear, we're trying to prove the diagonals of a rectangle are congruent. So I gave you this one. I labeled it rectangle ABCD. So, first step, we're going to need some triangles. That's the best way to go about this. There's many correct ways to go about this. They all follow about the same steps, just depending on how you pick your triangles, where you rotate them. You could even pick opposing triangles that share the diagonal AC if you're feeling fun, but yours is perfectly good. So, our first one, we picked these two triangles connected to our base AB. So, triangle ABC, which is ABC, which is this lower triangle, and then we have triangle ABD, which is right here. I suppose we should have labeled this a little bit better. Whoops. Technically, that's not correct, actually. Should probably be more clear. I said this was ABC. I should BAD, actually. Sorry, it should be more correct. Technically, was not a correct statement. Okay. So we have our two triangles. Then we can say the line segment they both share is congruent, reflexive property, or it's the exact same line segment. So of course it has to be congruent to itself. So then we can say angle DAB is congruent to angle CBA, which is both equal to 90 degrees. That's property of rectangle. We said that the interior angles are 90 degrees on our rectangle. Then we say DA is congruent to CB. These sides, again, another property of rectangle. It has to have two pairs of congruent sides. Once we have that, we have a side, an angle, and a side. So we can say that those two triangles are congruent using side, angle, side. Finally, we have this diagonal AC and diagonal DB. They are both the hypotenuse of triangles we said were congruent. So therefore, corresponding parts of congruent triangles are congruent, or CPC, TC, and we're done. We good? This makes sense? Clear? Snickering in the background? Talking about something more interesting than geometry? I doubt it. Okay, we're gonna do one more problem. We got some time. Okay, let's try and butcher this. Okay, what am I going to ask?
No question.
Oh, okay. So they're going to ask what?
CPCTC, does it work with other shapes?
Other shapes? Yes, if you prove they're congruent. So like, on these corresponding parts of congruent kites, I guess, are congruent. But yeah, it works as the same thing. It comes from like corresponding parts of congruent polygons are congruent. You'll never hear that term because it's just assumed when things are congruent, everything is the same. So then as long as it corresponds directly, aka you could just sandwich one on top of the other, You may have to rotate it, but just if you can sandwich it right on there and they're congruent, then they all have to be equal. Okay, really quick. Area of the triangle. Area of my triangle. The points of this triangle are 8, 7, 8, -3, and -4, -3. I'm going to pause here on this one. We'll give everyone a moment to draw it, think about it, figure it out. You guys have any art classes that go to draw better around here?
My little brother has one.
He has one? I didn't even think of that. Can't even get it through my tick mark. Maybe I should bring a ruler next time. Or a meter stick. It's getting a little ridiculous. You not like taking notes?
I came from somewhere else. I didn't have my notebooks in. But I know the answer sometimes.
I may ask you that in a moment. We'll give it another like 25 seconds. Other people. I am competent, I swear. I don't know what you guys are talking about. I dream about geometry in my free time. Sometimes. All the time. Sometimes. I just realized that wasn't recording too. Okay. Alright. Way more than 30 seconds. Area of my triangle. Before you just go for the answer, let's go for steps. What is a good place to start for my triangle? First step.
Subtracting, no actually, yeah, subtracting 7 and -5.
Okay. To make this a little bit easier, I will one close the door because people are being annoying. And then two, I'm gonna label these points. I'm just gonna label them A, B, and C, just to make it a little bit easier to talk about them. So, you said subtract 7 and -3. So, how about the difference of the y coordinates in B and C? So we could say that this line segment BC is equivalent to that. Okay? I like it. Next one, next step.
You can track the point x coordinate for B and A.
B and A. So I'd like the line segment BA. And I said, let's do 8 minus -4. Equals 12. Finish it off.
Then you just multiply them and then divide by 2.
So our triangle ABC, let's go with area. Area of our triangle ABC, let's say it's 1/2 times the base times the height. We said that our base is AB, so we'll say this is 1/2 times our AB or BA, it's 12. Our height is CB, BC, it's 10. 1/2 times 12 times 10. We can say it's 120 divided by 2. Do 60. We can also say it's 6 times 10 is 60. Either one works. You good on that? Alright, with that we will move on to some properties of quadrilaterals. So we did that little proof from before where we proved that the diagonals of a rectangle are congruent. By proof, there's a whole bunch of these for just all of them. So really quick, I'm going to draw a parallelogram, and I'm going to do properties of parallelograms. Okay. So really quick, things, whenever you see like something labeled with its name, these are what you can assume are true basically. They have been proven. They are always true. I'm going to label this APLR. APLR. So, things you can assume. The opposite sides are parallel. If you like to wonder why, it's by definition. When we say something's a parallelogram, it has to be that way. So I'll say definition. Our next one says the opposite sides all must be congruent as well. This isn't technically by definition, but we can prove that. Then the opposite angles are congruent because the opposite sides are. Okay, then the diagonals bisect each other. And these can all be proved. And then, any pair of consecutive angles are supplementary. Right, space. Whoops. Any pair of So, any pair of consecutive angles is supplementary. Basically, if I were to pick two angles in a row, as long as they're directly next to each other, or you could say two angles that share a line segment, the angles are going to equal 180 degrees. So, one more time. Not one more time. We're gonna go back to rectangle, and we will cover same thing. So, our number one precursor. Whoops, can't spell. All properties of parallelograms apply by definition. So we said that a rectangle is a parallelogram. So, if it is, all these are true by default. Then, all angles are right angles. And the diagonals are congruent, which we just proved. Okay. Any questions about parallelograms, rectangles so far? You good? These are just kind of good to knows for the homework and for future problems. Okay, the properties of a kite. I will butcher this. Give myself half second. Okay. Number 1. Two disjoint. So 2 disjoint pairs of consecutive angles are congruent. Two disjoint pairs of consecutive angles are congruent. The next one is the diagonals are perpendicular. And then here comes that one from rhombus that we're going to be using kite. The diagonals of our kite are perpendicular bisectors of each other. Okay, I guess I could just add that one in the 3. Okay, and there's a couple more about the diagonals of a kite. I am running out of space though. Let's do it right over here for a moment. So, one of the diagonals bisects a pair of opposite angles. And then pairs of opposite angles are congruent. Pairs of opposite angles are congruent. Okay. We're going to move on to rhombuses. I'm going to draw them higher up. Okay, I got it. Okay, so a rhombus is a type of parallelogram. So we can say the same thing from before with rectangle. All properties of parallelograms apply. By definition. All properties of kites apply by definition. Our next one is all sides are congruent. Or you could say a rhombus is equilateral. All sides are the same length. Yes.
What are two pairs of disjoint? No, two disjoint pairs.
Two disjoint pairs of consecutive angles. I will label it. Okay, let's label it just to make it easier to read. T-I-E-K. Okay, so if I labeled that, it's T-I-E-K, and you were asking the two disjoint pairs of consecutive angles. Did I say angles? I meant sides. Whoops. Sorry, I meant sides here. Sorry, I meant sides actually. That would be my bad. Whoops. Did I miss a note? What? There's more for this, yes. Sorry, I was just going to... Again, this is like the most unfortunate amount of writing I'm going to have to do. But these are basically a whole bunch of really great things to know, and also things that you can prove, aka could be on tests and or homework. Hint, hint. Wink, nudge, shove. All right, where was I? Rhombus number 4. Okay. The diagonals bisect each other. So many. Okay. And then the diagonals are perpendicular bisectors of each other. And finally, the diagonals divide it into 4 congruent triangles. Oh, right triangles too. Right triangles. Ooh. I'm sick of writing. Okay. Okay. Are people... I will leave this up for a moment for people to catch up on. But I will be erasing the ones over here now. The parallelogram. Yes. Someone doesn't know. If you need me to read any of them, I can. Number 6. Diagonals divide the rhombus into 4 congruent right triangles. Yes, please say something if you can't read them or need to write them. I will actually, here, I'll just read through all of them one more time before I start erasing. Yes.
Okay. If diagonals are perpendicular bisectors of each other, and why do you write it in rhombus? Why do you write it in rhombus?
Oh, did I already put it okay? Oops, my bad. Where is it? Yeah. Okay, I'll really quickly read through all of them, just to be clear. Our parallelogram. When we have a parallelogram, all the sides are parallel. All the sides are congruent. All opposite sides are congruent. Opposite sides are parallel and opposite sides are congruent. I'm going crazy. Opposite angles are congruent, and then diagonals bisect each other, and then any pair of consecutive angles is supplementary. Okay? For rectangles, all properties of parallelograms apply. Angles are right angles. The diagonals are congruent. As for kites, the two disjoint pairs of consecutive sides are congruent. The diagonals are perpendicular, and then the diagonals are also perpendicular bisectors of each other. Finally, one of the angles bisects the pair of opposite angles. And then pairs of opposite angles are congruent. As for rhombus, all properties of parallelograms apply. All properties of kites apply. I definitely repeated one. Actually 2, I believe. But all sides are congruent. The diagonals bisect each other, which I think is... Diagonals are perpendicular bisectors of each other, and then the diagonals divide the rhombus into 4 right triangles. We're almost through these. I think there are 2 more. There are 2 more, thank goodness. So, really quick, properties of squares. Properties of rectangles. So really quick, for square, we only have 2 more. We have squares and trapezoids, specifically the isosceles. So, our first starting one is, for squares, that the properties, yes.
Can you explain number 4 for kite?
Kite. One of the angles bisects a pair of opposite angles. I'll label it, just to help out. Oh, I have it labeled. Perfect. So,
They put angle. It should be that.
where?
On 4, they put one of the angles.
I think you're right. Yeah, you're right. That sounds kind of weird, an angle bisecting. Yeah, sorry, it's when the diagonal bisects a pair of opposite angles. Which is not bad. Yeah, I actually even. Whoops. Oh, I'm tired of writing. Okay.
No.
4. Isosceles. SOSC.
No. See? It's like so good. It's like
4 congruent. Isosceles, right? They're also congruent. That's okay. Okay. Okay, properties of square, really quick. Properties of rectangles apply. Properties of rhombuses apply. And then diagonals form 4 congruent isosceles right triangles. And then let's do isosceles trapezoids. And then we can call it. I'm rewriting. Okay. So our first one, whoops, is that for our isosceles trapezoid, the legs are congruent. Our second one is that the bases are parallel. And our next one is the lower base angles, which again are these little ones right here, are congruent. With that, the upper base angles are also congruent. I jumped from 3 to 5.
I'm listening.
All right, and the diagonals are congruent. Last one. Ugh. Okay. Finally. I'm done there. Okay. Really quick for isosceles trapezoid, got a couple properties. The legs are congruent, the bases are parallel, the lower base angles are congruent, the upper base angles are congruent, our diagonals are congruent, and then either lower base angles can, no, that's not, it's supplementary. Supplementary. Any lower base angle is supplementary to any upper base angle. So basically, if you pick a lower base angle and you pick an upper base angle, they will equal 180 degrees. Are we good with all of these? I know it's a lot of writing. We shouldn't have to address these. Are we good to go then? Oh, sorry. Definitions. Okay, now having gone through an entire thing of assumptions. Oh. Are we good on these two? Can I erase these?
Yes.
Move on? Thank goodness. I didn't like them anyway. Please do not die. Ooh. See you guys. ABE, CFP, okay, so we're going to do one more problem, and this will be another one of the proofs. So this one we're going to do 2-column proof. So prove. So I'm going to say I want to prove that GH is congruent to line segment EF. Yes. Okay, I'm gonna say given that ABCD is a parallelogram. angle GHA is congruent to angle FEC. Yes. FEC. And then HB is congruent to DE. Okay. Okay, I'll give you guys a couple minutes. And we'll go over it and homework and done. Close? Got it? Some people ready? Thinking about it? Give it 30 seconds. We ready? There you go. Almost close. Okay. All right. Anyone, first step. Or I should say, what is the best step to start with when given, rightly given? I like it. Oh, I'm gonna use this first one. A, B, C, D is a parallelogram. Okay, good first step. How about the next one? Second step?
You can say that A is equal to EC because it's given that HB is equal to DE, and if you subtract it from E.
There's a couple steps, just to warn you. What? Just how?
So if you subtract these, if you subtract EC, DE, if you subtract DE from DC, you'll get you get EC, and if you subtract HB from BA, you'll get HA, and because HBA and CD are congruent because they're opposite, and DE and HB are congruent because it's given. HA and EC are congruent.
HA. G.
HA.
HA.
HA and
So what about GH?
and then after that because AC it's kind of like a transversal, so the opposite interior angles GAH and FCE are congruent. And then
So what does that say about the whole? So if I were to tell you, I see where you're going. Actually, yeah, you can continue. Okay.
and then because you have because GAH GHA and the line between AH is and because you have those three, and same for the other triangle, you can use SAS to say that those triangles are congruent, and then you can use CBCDC to say that EF and GH are congruent.
Okay. Okay, that was a whole bunch of steps, slightly out of order. I'll give you a little bit more order to this, just so you're not jumping around. So I'll start out with how about the parallel sides? We said it was a parallelogram. Let's say that AB is parallel to DC, and oops, it's not number one second time. Properties of parallelogram. Okay, I'm gonna use what you said from before. I think I'm gonna go with an angle side angle instead of side angle side. Again,
No, I
yours
did-
was fine.
I did use angle side angle. This GH.
You said side angle side, right?
This is angle side
You
angle.
said, oh, okay. I'm gonna use angle side angle because I like this. We said that our diagonal bisects an angle, or you can use a transversal across parallel lines. Both are fine. Alternate interior angles, so they're congruent. So I'm gonna say that GHA. GAH, I'm sorry, GAH is congruent to FCE. And I'm going to say alternate interior angles. Alright, so I've got G, H, E, F. Oh, sorry, that's not improved. I'm crazy. H, B, D, E? Okay. Alright, so now I'm going to use one more. You're doing subtraction on the bottom? Okay. We'll go in that order. I'm going to say that AB is also congruent to DC. Property, properties, parallelogram. Then, running out of time? We're running out of time. Okay. Now, I'm going to say, ooh, I need this one. I didn't write this. I need to write my given one more time. I didn't write this one from earlier. I'm going to need it right now. I need to know that HB is congruent to DE. It's another given. Because I want to be able to say that AH and EC are the same. This is subtraction property. Yeah. Subtract one. If they're congruent, we know a congruent singular part. We know the last segment is also congruent. Subtraction property. Okay, we're almost there. I'm just going to say step 7 is we're going to take our angle one again. GHA is congruent to angle FEC. It's another given. And now we have congruent triangles, so we can prove it with angle side angle. Triangle HG is congruent to triangle CEF. That's 7 is, I can't write, angle side angle. And that was number 8, not number 7 again. Finally, number 9, we can do our proof. GH is congruent to EF, CP, CTC, and we're done. So, there you go. Homework real quick. You guys free to go? Sorry, I was just giving him a little bit more coherence instead. But you were right. It's just when you backtrack, you're like, oh, wait, oh, I need this, I need that, then I can get there. That's fine.